Welcome back, everybody. So we're going to start chapter 6, which is going to be on volumes and areas, and the first section is the same as last year. We're going to start with finding the area between two curves. So for our two curves, there's going to be two scenarios, of course. One where we have two functions of x, where one function is clearly larger than another function on a given domain. And we're just going to calculate the area between them, taking the height of a rectangle and then some fixed width. So same as our integration, only instead of using the x-axis as our bottom function or top function, depending on where we're located, we're going to actually do it between two curves. But what we end up with is essentially the same process of integration, where we're going to have an infinite number of these rectangles, take the limit as the width shrinks down to 0, and find the area between. So we've got our Riemann sum representation here, and then our integral, definite integral, which we're going to be using to evaluate. If we have functions of y, the only thing that changes in our orientation is that our rectangles will be horizontal, which means that our height will be measured horizontally. And whereas functions of x, we're going to use the top minus bottom, so the function with larger y value minus the function with a smaller y value. For functions of y, it's going to be the opposite. It's going to be the larger x value minus the smaller x value, which will be right minus left, since to the right, x is getting larger. Okay, so let's go ahead and just jump into some examples here. So we want to find the area enclosed by the line y equals x minus 1 and the parabola y squared equals 2x plus 6. So in order to start, what we can notice to begin with is that we've got a function of x, and this is f of x equals x minus 1, and this is going to be f of y equals something, right? So if we solve this for x, we'll get 1/2 y squared minus 3, right? So we've got a function of x, function of y, and that's going to be a bit of a problem because we can't integrate functions with different variables as our independent variable. So we're going to have to make a choice. It's either going to have to be a function of x scenario or a function of y scenario. So if we graph both of these functions, the x minus 1 graph, of course, is going to be the line passing through 0, -1, 1, 0. And we can do the same thing for our parabola, right? Graph it by intercepts. So if y is 0, x is -3. And then if x is 0, y is going to be plus or minus rad 6. So, and we know it's a parabola that is got a positive leading coefficient. So it's going to be opening to the right. So we know it's going to be opening to the right, so we use that information to graph. Our parabola here. So we've got -3, 0, and then rad 6 is going to be between 2 and 3. And we'll end up with the parabola. Oops. That looks something like that. And so here we can pretty quickly tell whether we want to use vertical or horizontal rectangles. So if I choose vertical, right, it works pretty well over here, but then there's going to be this dividing line. Right, so note it's blue minus red for the height at every point, right? Parabola minus line. But then here it becomes parabola minus parabola. So that means then that we're going to have two separate areas to evaluate, which we can do, but we have to use two integrals. So if we go back and look at the horizontal rectangles, perhaps we'll get a better outcome. And we can see, yeah, if I do horizontal rectangles, it's going to be red minus blue now, right minus left. And I can do it all the way from the top of the intersection to the bottom intersection. So I think we're going to want to use a function of y here. Now we do need to know where the intersection points are. So to find our intersection points, we'll set our equations equal to each other. So we'll note x equals y plus 1 is our function of y. And as mentioned earlier, y squared, x equals 1/2 y squared minus 3 is our other function of y, our parabola. So if we set those equal, we got y plus 1 equals 1/2 y squared minus 3. Move all of our terms over. Minus y minus 4. Multiply by 2 to make the factoring a bit easier. And it looks like -2 and 4 are our two intersection points. So looking at our graph, my graph is somewhat close to that. So we've got 1, 2, 3, 4 is up here. Let's try that again. 1, 2, 3. So I'll put 4 as that intersection point, and then 2 as that intersection point. So those are my two intersections. And we're going to be integrating along the y-axis. So it's going to be the integral from -2 to 4. All right, so let's go ahead and set up our integral here. So we've got the area is equal to the integral from -2 to 4. The right function is the line, which is y plus 1, minus the left function, which is 1/2 y squared minus 3. And that's going to simplify to -1/2 y squared plus y plus 4. And now we just need to evaluate from at 4 and at -2. So we're going to get -1/6 y cubed plus y squared over 2 plus 4y from -2 to 4. Let's go ahead and work this out. So we've got -1/6 times 64 plus 16 over 2 plus 16. So that's going to be our capital F of 4 antiderivative. And then at -2, we'll get, looks like 8 over 6 or 4/3 plus -2 squared is going to be 4 over 2 is 2 minus 8. And so let's go ahead and finish evaluating this. So -1/6 times 64 is going to be the same as -32 over 3. We've got 8 plus 16 here, so that's going to be 24. And then we've got minus 4/3. And then 2 minus 8 is going to be -6, so the opposite of that is going to be +6. All right, so let's see here. So we're going to have -36 over 3 plus 30, which looks like it's -12 plus 30, which is 18. So our answer is going to be 18 for this one. Okay, so a bit of work here. I wanted to start with this example as a function of y just to emphasize that you're going to see functions of y from time to time, and it won't always be the simple functions of x that we're used to. Below that, I've already graphed the areas on the remaining examples. So for number 2, find the area enclosed by the graphs y equals x squared minus 6 and y equals 12 minus x squared. So same as the first example, we would start with setting those integrals equal, or sorry, setting those functions equal to each other. This one's clearly going to be a function of x example, top minus bottom. And so if we solve, we'll get 2x squared is equal to 18. So it looks like x squared is equal to 9, so x equals plus or minus 3. Now, I still highly, highly, highly recommend drawing graphs, even if you know what the general graph is going to look like. For all of these examples, definitely don't use a calculator. Get a little bit of practice in without using your calculator here. So -3 to 3, and we can clearly see there's not going to be an issue with having to split the range, the area into multiple pieces. So top minus bottom is going to work for us. And we have symmetry also. So we can actually use the even symmetry of both of these functions to make our integral easier. So we know we're integrating from -3 to 3. So the area is going to equal the integral from -3 to 3. My top function is the 12 minus x squared. And my bottom function is x squared minus 6. And so you could evaluate that as is, or you can use symmetry. Since you've got even symmetry about the y-axis, you could just double the integral from 0 to 3, and then you don't have to worry about the messiness of figuring out what your antiderivative is at -3. So I'll just simplify the inside a little bit here. Looks like we're going to have negative x squared plus 18. And again, I'll leave that for you to do on your own. You can check the answer in the notes online. For number 3, we've got another parabola, and then we're going to bound it by its tangent line at 1, 1. So I drew a picture on the left here, but it's kind of hard to see the region, so I tried to zoom in a little bit there. So it's that little sliver of space. But we can definitely see that the tangent line will be below the graph, and we're bounded by the x-axis. So it is definitely important to remember the boundary points. So as a separate case, we could have a function that, say, looks like this. And maybe it looks, I don't know, something like that, right? So let's say from 0 to some value a. And in this case, for these 3 regions here, we would need 3 different integrals. So definitely be careful with how many areas you have, or again, we might simply say, okay, let's call this C. Just find the integral from C to A, or C to B, B to A, so we can find any of those specific areas if we wanted to separately. So for this one, we just need to figure out what the tangent line is. So we know that y prime is going to equal to x, and then at 1, you're going to get 2, so you know the slope of the line is 2. So our tangent line is going to be y minus 1 equals 2 times x minus 1, which is 2x minus 2, so 2x minus 1. Okay, so y equals 2x minus 1 is the bottom curve. But what you'll notice, right, is in that region, when y is 0, x is 1/2. Let me actually highlight here that. So there's going to be an area from 0 to 1/2 that is just bounded by the x-axis. And then there's going to be the other area until 1 that is going to be the area between. So we actually need two integrals for this example. So the area then is going to equal the integral from 0 to 1/2 of x squared dx plus the integral from 1/2 to 1. And now we would use our normal top minus bottom. Let's see. So that's going to be x squared minus 2x minus 1. And you can go from there. Or, if I wanted to, I could also make this a function of y example. So note, you could work this one out. But if I did functions of y, we would get x equals radical y, and it would be the positive radical y since I care about the right-hand side. Right, so x is always positive. And then my 2x minus 1 would become 1/2 y plus 1/2 equals x. So I could do right minus left also. And the boundaries would be the same. You'd still be integrating from 0 to 1. So the area, if we did it as a function of y, would be the integral from 0 to 1, 1/2 y plus 1/2 minus radical y dy. We'll do brackets. Okay. So now two options here. Same answer regardless. But again, it looks like that function of y is going to be an easier example to work out. And again, you can check the notes online for the correct answer. And then finally, we've got number 4. So we've got a parabola that is bounded above by the line y equals 4. And we want to put a horizontal line in that's going to separate our parabolic area above and below into two equal parts. So we want them to be congruent areas. So if we think of each one separately, area of 1 is going to be the integral from b to 4 of what? Right? So that would be along the y-axis. Okay. So we could do that. And if we do that, right, then our height is going to be 2 times the parabola's height, since we're symmetric. So this would be x equals rad y. So we could do 2 rad y dy. Okay, and then area 2 could equal the integral from 0 to b of 2 rad y dy. And we would set those equal to each other by evaluating. We should get some interesting result from it. But let's also think, well, suppose we want to do this as a function of x. Could we do this as a function of x? Right, so this would be the function of y representation. For the function of x, okay, so let's see. So we would have area 1 would be the integral from, from where to where? So here's where we get a little bit tricky, right? There's these little spaces here where it's not bounded the same way. So it would depend on where the parabola, reaches b. So if x squared is equal to b, x is equal to radical b. So it'd be plus or minus radical b. So we could do that. So we get negative rad b, positive rad b, and then it would just be 4 minus b dx. But then we need to add these little slivers on the end, which would be symmetric. So we'd have 2. We could just do double the one on the right. From radical b to the intersection of y equals 4 and x squared, which is at positive 2 on the right. And that would be 4 minus x squared dx. Okay, so we could do that. You can see that that's going to be a bit messier, but it would still work. And then area 2 would just be 4 minus x squared. So let's just put it above here. 2 would equal integral from, and the intersection would again be negative rad b to radical b of 4 minus x squared dx. All right, so here's our f of y case, here's our f of x case. So you can decide which one you want to try and see which one works out. It's looking like the function of y example is going to be much easier. So let's go ahead and try this one and see how far we can get. So we've got the integral from 0 to b, 2 rad y dy equals the integral from b to 4, 2 rad y dy. So if we anti-differentiate, y to the 3/2 times 2/3 is going to be 4/3. And then scoot over here. We'll have same thing from b to 4. So we'll get 4/3 b to the 3/2. At 0, it's just 0. And then, well, 4/3 times 4 to the 3/2, which is 4 cubed is 64. The square root of 64 is 8, so it's going to be times 8. And then it's going to be subtracting that same 4 over 3b to the 3/2. So we could add that over. And we can multiply by the reciprocal here. So it looks like b to the 3/2 is going to equal 4. So b is going to equal 4 to the 2/3. Or the cube root of 4 squared, so the cube root of 16. And that would be our solution using that function of y example. All right, so this kind of covers the intro to area between curves. Again, you'll be doing examples in the homework as well to kind of review. So if you have any questions, shoot me an email or come by the office hours. Until next time.